And it's my pleasure today to welcome Dr. Shirley Wang, who's going to be giving today's lecture. Dr. Wang is an associate professor of medicine at Harvard Medical School and an associate epidemiologist in the Division of Pharmacoepidemiology and Pharmacoeconomics at Brigham and Women's Hospital. She's focused on developing innovative and non-traditional analytic methods to understand the safety and effectiveness of medication use in clinical care, as well as facilitating the appropriate use of complex methods for analyzing large observational healthcare data. She's worked extensively with ISPI, ISPOR, and she also launched the REPEAT initiative, which is a nonprofit program with projects designed to improve the transparency, reproducibility, and ability to assess the validity of healthcare database studies. And it's, I'm very, very grateful for her to be giving today's talk, which will be entitled Tools to Increase Transparency, Reproducibility, and Validity of Real-World Evidence Studies. So with that, Shirley, the floor is yours. And we'll, Dr. Wang will be giving her presentation, and we'll then have a Q&A session where you can either post your questions in the chat or use the hand function and unmute yourself for questions.
Okay, thanks. So as Chris said, I will be talking about some recent efforts and tools to encourage greater reproducibility and transparency for studies that make secondary use of routinely collected clinical practice data. So today I plan to sort of talk at a high level about 4 topics, but before diving into those, I'll just briefly touch on why this is so important. So reproducibility as a principle is very important. There have been concerns about lack of reproducible research in many scientific fields, including cancer biology, psychology, economics, bioinformatics, as well as clinical trials. And recently, there have been some large-scale efforts to evaluate the reproducibility of studies in these disciplines, with results that suggest there's room for improvement, and our own field is not exempt from this. So for many of us, the end goal of generating real-world evidence is to help inform decisions about the benefit, harm, or value of medical interventions. But to do this, we need to have confidence in the scientific approach. Is it valid? Is it robust? And is the evidence transportable to different populations? And in order to have that confidence, we need to understand how the evidence was generated. And it's at this foundational step that we have a hurdle to get over, because the lack of clarity in reporting has been a barrier to using real-world evidence in decision-making, because ambiguity about how the evidence is generated makes it difficult to reproduce findings, to assess the validity of methods, and also to evaluate the relevance for the question of interest. So I'll start by talking about the REPEAT initiative, where we've recently completed a project where we attempted to independently reproduce 150 published descriptive and comparative effectiveness or safety studies by applying the same methods to the same research databases as reported by the original investigators. So we carried out these study reproductions blinded to study results in order to maintain independence. And when a scientific decision was not clear, we had a system for making and documenting our assumptions. So independent reproducibility requires unambiguous communication about a study's scientific decisions. So we were trying to evaluate how clearly these decisions were communicated from public protocols, publications, and appendices, and then see how that related to our ability to reproduce studies. So in this reproduction effort, generally what we saw was that for the majority of studies, we were able to reproduce the results pretty closely. But there was also a substantial minority that we weren't able to reproduce closely, even when using the same data sources and trying to implement the same methods. There were 3 main reasons why we had difficulty reproducing studies. First, we struggled when there was incomplete information on details of key design parameters, particularly noting the lack of clarity regarding when study parameters were measured relative to the study entry date, as well as the absence of detailed code algorithms. And second, we struggled when there was incomplete information about data version. We did try to use the same years of data from the same data sources as the original authors, but the data aren't static. There can be retroactive updates to the data that can shift the underlying population, as well as how certain variables are populated. As an example, we know that one of the data sources we used changed how death was captured in different ETLs. In one of the versions, they did not include deaths from the Social Security Death Index, and in another, they did. And a third reason that we struggled to reproduce studies was sometimes, we saw internally inconsistent information between the text, attrition tables, and the diagrams, which forced us to make assumptions about what was actually implemented. So through the Repeat Initiatives Reproducibility Project, we tried to identify areas where current levels of communication about study design and analytic decisions fall short of what's needed to fully understand how the evidence was generated. We also observed in our sample the continued publication of real-world data studies that clearly suffer from avoidable design flaws. And because I'm going to spend the rest of this time talking about tools for increasing transparency to enable validity assessment, I just want to briefly emphasize that transparency is not equal to high study validity. And here's a 2x2 table to highlight that point. I mean, the goal is to have transparent studies where the methods are documented and communicated in detail so that others are able to assess validity and reproduce findings. But these are transparency and validity, they're separate concepts that don't always co-occur. And we did see with the Repeat project that we can reproduce bias studies very closely if the study implementation decisions are clear. But when those decisions are not clear, even well-designed studies can be difficult to reproduce or assess for validity issues. So in order to facilitate communication and increase reproducibility, we had proposed this framework for graphical depiction of study design a few years ago, and I'll just quickly describe this framework and provide a few examples. But before diving into study design visualization, I just wanted to quickly talk about what we typically see in our source databases. As you know, we capture things when there's encounters with the healthcare system, such as associated diagnoses, procedures, prescriptions, notes, and other documentation. And this information can be visualized longitudinally in calendar time with lines representing points in time, such as an outpatient encounter, and wider intervals representing duration of inpatient stay or day supply. And as shown here on the left, patient history across calendar time can be visually represented for multiple patients in the data. But when we do our research studies, we need to create analytic data sets that are anchored on patient event time. And that's shown in this right-hand figure where time is now anchored around a first prescription of a drug of interest, which is denoted as time 0. So this alignment of person time anchored on a patient event rather than calendar time helps us to be clear about what is measured in baseline versus follow-up. In the end, what we typically analyze is a clean flat file consisting of mostly ones and zeros. But in order to appropriately interpret from the findings from these types of studies, it's important for reviewers and decision makers to understand how that series of ones and zeros was created and whether there are any validity issues that would change their level of confidence in the results. And this is where design diagrams can be helpful as a way to concisely summarize and communicate some of those key design parameters. So in the NL's paper that introduced this graphical framework for representing study design, we provided a brief glossary for study time anchors where base anchors are defined in calendar time and describe the source database. First order or primary anchors are defined in patient event time, and they specify time 0 and other key anchor points. And then second order anchors, like windows to measure inclusion, exclusion, covariates, washout, or follow-up, are defined relative to the primary anchor. And I won't go over these in detail, but you'll see them in the examples in a moment. I'm just going to go through a few at a very high level. As a side note, there were some PowerPoint templates that were published with the paper, or you can use a web-based RShiny app to help create publication quality figures to scale. So here's an example diagram for a very simple, straightforward study that evaluated the risk of angioedema with ACE inhibitors compared to angiotensin receptor blockers. And on the left here, I've highlighted the methods section describing the study design. All of this information is then represented in the diagram, which is intended to be read from top to bottom, showing the sequence of actions taken to create the cohort. And the vertical gray arrow is used to represent day 0, the point at which the study entry defining criterion is met. And then the size and location of the horizontal bars visually show the assessment windows for the inclusion-exclusion criteria, covariates, and follow-up relative to day 0. In addition to the visual representation, there's bracketed numbers within each bar that use standard mathematical notation to explicitly specify temporality. So the diagram can also be helpful in spotting potential validity concerns. For example, if you were to see a covariate assessment window that stretched from before cohort entry into follow-up, this could catch our attention and lead us to carefully consider whether we might be concerned about looking into the future to measure baseline risk factors or adjustment of causal intermediates. The design diagram could also help identify issues with the mortal time bias. I'm showing here a classic example of a cohort study that was used to evaluate statin use and risk of diabetes progression. And without going into the details, you can see that there's a lot going on with exclusion criteria and exposure being assessed after follow-up begins. And this hopefully raises flags to look carefully at how the analysis was handled. So Dr. Levesque and her colleagues described in detail that there were 3 windows of potential immortal time in this analysis, all of which could have been alleviated with a time-varying analytic approach to handling exposure status, but that was not the case for the study that implemented this study design. So the visualization framework can also be used for case control studies, self-controlled designs, and more complex cohort designs with multiple primary anchors, as might be needed for pregnancy studies. In a paper by Laura Happy, who's editor of JMCP, she found that only 42% of the real-world evidence studies published in her journal had any kind of design diagram at all, in spite of this being strongly recommended at the time of submission. And as an exercise, she tried using this visualization framework to diagram the design for 2 studies that were published in the journal, and noted that the ambiguity in the manuscript text did not permit her to diagram the study design with confidence that the diagram would be an accurate reflection of what was actually implemented. So that brings me back to the case for using design visualization to try and increase transparency and facilitate reproducibility. Design visualization is a tool that can be used when planning the study to help the investigator think about time and measurement windows and potential biases. And then having prepared this in the planning phase, the visualization becomes a reporting tool to help facilitate unambiguous communication. And once shared, it provides end users with key information that's needed to make assessments of validity. So while we're on the topic, I just want to quickly mention an enhancement to the design visualization framework that Sebastian Schneeweiss and I've been working on. So the original framework captured the temporal anchors for study design relative to time 0, but didn't incorporate any information to help readers assess the appropriateness of the source data, such as whether the data were observable during the assessment windows. And this is particularly relevant for US-based EHR databases, where we expect to see at least partial unobservability in longitudinal data because of the fragmented healthcare system. So to illustrate this point, in this figure, I'm showing you a diagram based on a real study that was looking at the comparative effectiveness of famotidine versus non-use on the risk of death for hospitalized COVID-19 patients. And the design was relatively simple. Day 0 was the date of the admission to the hospital. Exposure to famotidine was assessed on the date of admission. The investigators looked back 90 days as a washout for prior famotidine exposure. They required patients to have lab-confirmed COVID results between 14 days prior to 3 days after hospital admission. They excluded patients with use of intensive services within the 90 days prior to or on day 0, the date of admission. And for covariates, they assessed risk factors for death in the 90 days on or prior to admission. Follow-up began 1 day after admission and continued until death, discharge, or the end of the study period. So this is all very well and good, but we know that a design that is fit for purpose in one data source may not be in another. So the revised design visualization framework adds in some information on data observability. This is color-coded as observable in dark pink, not observable in light pink, and incomplete observability in dashed dark pink lines. So I know I just whizzed through the study, but let's say it was conducted using Premier, a hospital EHR-based research database. So when these observability lines are superimposed on the design diagram, we can quickly see that exposure on the date of admission is observable, but the windows for assessing prior use of famotidine, lab confirmation of COVID, prior use of intensive services, and risk factors for death are stretching over patient history that is only partially available in this data source. This is because Premier is an in-hospital EHR data source. It doesn't include outpatient diagnoses, procedures, drugs, or lab results. And the only way that this baseline information could be captured through the data is through data that's available on the date of admission or through recent prior hospitalization in a hospital that's also part of the Premier database network. So if the design were applied to a linked claims EHR database, you might see more dark pink lines indicating complete observability overlaid on the design diagram because patient baseline information would become observable in the data through the linkage to claims. Alternatively, if the investigator was not able to access different data and had to stick with the in-hospital only EHR database, use of the design visualization framework might prompt them to modify the design parameters so that they don't provide a misleading impression about the amount of information that's available to evaluate inclusion-exclusion criteria and covariates. So in this slide, when using the Premier hospital-based EHR data, the washout for prior use of famotidine is removed from the design because that information on prior exposure is simply not observable. And this turns the study into one that compares prevalent use versus non-use in hospital among patients with uncertain prior exposure. The windows used to assess lab-confirmed COVID, intensive services, and risk factors are also shrunk to only reflect hospitalized time during which patient healthcare transactions are observable in the research database. So moving on to the next related workstream that I wanted to talk about today. As you may already be aware, the International Council of Harmonization, ICH, which is a nonprofit organization that brings together international regulatory agencies and pharmaceutical companies, has a short-term strategic priority that's focused on harmonizing the technical and scientific requirements for studies that are submitted for regulatory consideration. So this prompted the formation of an ongoing ISPI-ISPOR Joint Task Force, which is focused right now on creating a harmonized protocol template for comparative real-world data analyses. So in our initial months, we focused on doing a landscape review of prior and parallel work streams, where we searched the Equator Network, PubMed, ISPI and ISPOR resources, as well as used snowball identification of real-world evidence protocol templates through experts. We identified 4 templates that were developed by international multi-stakeholder groups to harmonize across. And these included the EMA PASS template, guidance from ISPI's good pharmacoepi practices, the NESCC protocol guidance, and the START RWE template. The task force met roughly monthly over the last 18 months to develop the harmonized template. And the process included both evaluation of external validity through comparison of existing templates and internal validity through testing and development of example use cases with different designs and data sources by 5 subteams. So after reviewing these, we realized that there's been a lot of activity from different groups, but there's no major discrepancies in the overarching principles. However, there is variation in the level of detail or the standard of transparency set by different tools. Here we've mapped the sections of these 4 protocol templates to each other, highlighting the commonalities as well as the different structure and information content requested. For example, 3 out of 4 templates had section headings with a few sentences or a paragraph of guidance of what to include in those sections. This gave the user complete flexibility in terms of free text entries under those section headings. The 4th, the START RWE template, used structured tables to guide the users on where, what, and how to specify study implementation details. This last template also had a strong focus on clearly delineating time 0 for entry to the study population, as well as orienting baseline and follow-up windows around that primary anchor. So the goal with this joint task force was to try and harmonize across these templates and set a common standard for transparency in the form of a protocol. We developed examples for a variety of use cases, including an active comparator new user design effectiveness study, a nested case control study, an example of a new oncology therapy compared to standard of care, a pregnancy safety study, and a self-controlled case series. The work is still ongoing, but we're aiming for the deliverable to align with the ICH timeline for producing recommendations. That said, the harmonized template is intended to be broadly applicable to both pharmacoepi and outcomes research outside of regulatory purposes as well. So to go into a little bit more detail about what this looks like, Harper, the harmonized template, gets into the weeds of doing the real-world data analysis. And I won't go through all of the details, but I'm just going to try and give you a relatively high-level overview of the contents. There's 5 major sections, plus some administrative components that I won't cover. The first of these sections is a table to describe amendments and updates, because the protocol is a living document over the life cycle of the study, and it's important to keep track of what changed and why the changes were made. For example, over the process of developing and implementing a protocol, you might have an initial version for doing an initial set of feasibility counts, looking at outcomes that are not stratified by exposure. In version 2, you might use revised algorithms and do some diagnostics like assessing balance and propensity score variables. And in version 3, using finalized algorithms to implement the actual analysis. The sections on rationale and research question and objectives are a combination of free text and structured free text prompts to encourage inclusion of important key contextual information. For example, there's a paragraph about the condition being investigated, information on the exposures, where the gaps are, and the expected contribution from the study described in the protocol. The prompts also ask the user to summarize PICO information, the population exposure comparator outcome and time horizon for the study. Now, research methods is the bulk of the protocol. I said there were 5 main sections, but for section 4, there are numerous subsections where each is structured in the same way, where there's a free text part to lay out context and rationale for the scientific choices, coupled with a section that uses either tables or a figure to provide details on operational definitions. For example, in sections 4.1 and 4.2, there are structured free text prompts that ask the user to name the design and rationale for the choice of design. And this is coupled with the design diagram that we talked about earlier. This diagram provides a concise visual summary of how the analytic cohort was created, almost like a visual abstract. And without going into the technical detail, the subsections underneath detail in a very structured way the context, rationale, and operational definitions for key study parameters such as day 0 for entry to the study population, inclusion and exclusion criteria, covariates, outcomes, and as also the context and rationale for these choices. So in these tables, it summarizes what's measured, the timing of measurement, the care setting, the types of codes that are used to define the measure, as well as the sources for the algorithms, whether they're from a publication or clinician review. For algorithms based on diagnosis codes, there's also a section to define whether codes are required to be in the primary position. And then the actual clinical codes are specified later in structured machine-readable appendices. Each table in the method section also includes fields to indicate whether the study parameter was pre-specified, whether it was varied for sensitivity, and the source of the algorithm to define that measure. So on this slide, I'm showing you free text and table sections focused on detailing the time 0 defining criteria for entry to the analytic study population. Similar free text fields for context, rationale, and tables for operational definitions are used for the inclusion-exclusion criteria, exposure, outcome, and covariates. And I'm not showing it to you on this slide, but in the covariate table, there are also fields to specify things like how the variables enter models, for example, continuous, binary, or categorical. And in the outcome table, there's also additional fields to specify the performance or validation of outcome algorithms, as also to indicate which is the primary and which are secondary outcomes. The follow-up table is set up a little differently. Here there's structured fields to define when follow-up begins relative to cohort entry and how it ends, which helps the investigator to consider each option and make an active choice. And it also makes it clear for the reviewer what is and is not used to end follow-up. You can see on this table that there's fields to indicate a variety of conditions that could end follow-up, such as death, disenrollment, a fixed calendar date, or end of exposure with prompts to provide details. For example, details on how duration of therapy is defined, where it can be helpful to specify decisions regarding how to handle early refills or bridge short gaps in between dispensations. So following the sections about study design are sections about the data sources being used. Again, there's a free text section for context and rationale, followed by a structured table. The free text includes structured prompts to state the reasons for selecting the data source, the strengths and limitations of the data, and information about the data source provenance or curation. This section is also where a detailed evaluation of the fitness of the data in relation to the study question can be provided. The particular table here asks for metadata about the data sources, including things like the data source name, the data version, the extraction date, sampling criteria if that's relevant, and information about data linkage or conversion to a common data model can be summarized here with more detail in appendices if needed. So there are also sections about the study size and data management plans, which I won't talk about, but this is followed by a data analysis section where the primary, secondary, and subgroup analyses are specified. So this table includes fields for the hypothesis being tested, software packages, the models that are fit, the type of confounding adjustments, with prompts for specification of key parameters such as the matching ratio and caliper, formulas for weights, trimming and truncation rules. Also reported in this table are fields through these fields for missing data about how it's handled in the analysis and as well as subgroup analyses. It sort of ends with a structured table for detailing what sensitivity analyses will be conducted and the rationale for conducting them. In other words, being explicit about what you intend to learn from doing the sensitivity analysis. This rationale is especially important to help end users make sense of and interpret the findings, particularly in a discipline where it's easy to run many sensitivity analyses. So the last section of the template are the appendices, where structured human readable tables in the template are intended to be accompanied by the machine readable appendices that list out the actual clinical code algorithms that are used to define the study parameters. And these can be accompanied by appendices to detail other things like the decisions that are made when converting source data to a common data model or doing data linkage. So you can see in this example of a machine readable appendix, each condition is named in the first column, a clinical code in the second column, the type of code described in the next column, and then a description of the code follows. So this type of appendix can be helpful when you need to double check your algorithms and can also be read directly in by programming code when you're creating an analytic cohort from source data. So to summarize, currently there's ambiguity in communication of key study parameters that can sometimes make it difficult for reviewers to assess potential for bias. And this can limit the utility of real-world data studies in healthcare decision-making. So the harmonized template builds on existing efforts to improve transparency and incorporates recent insights regarding the level of detail needed to enable real-world data study reproducibility. The overarching principle was to try and reach for sufficient clarity regarding data, design, analysis, and implementation to achieve three main goals. And these were first to help investigators thoroughly consider and document their choices and rationale for key study parameters. Second, to facilitate decision-making by enabling reviewers to readily assess potential for biases related to these choices. And three, to facilitate reproducibility. So the template itself can be used as part of a backbone throughout the research process, from developing the initial protocol to registration, through implementation, and then reporting on those implementation decisions. It tries to create a shared understanding of the intended decisions through a common text, tabular, and visual structure, so that multidisciplinary teams and reviewers of their work will know what to look for and where to look for it. So the task force recognizes that the impact of the harmonized template relies on uptake. So we're in the midst of outlining a plan to introduce and pilot it with international stakeholders over the next few years. First, we are seeking endorsement from ISPI and ISPOR as part of this joint task force. So for those of you who are society members, you can expect to see requests for member comment coming soon. We're also in communication with NCEP in Europe to have this folded into the revised guidelines for next year. The template is also going to be used for a demonstration project with the Sentinel program's causal inference framework. And we're in the early stages of discussing potential piloting the use of the template with other ongoing projects with EMA, EU HTA networks, and others. So if there would be an opportunity to explore using the template with CNODES, we'd love to talk about it. And finally, I just want to briefly mention the Real World Evidence Registry, which was a product of a multi-stakeholder steering group led by ISPOR in partnership with ISPI. And that work stream was focused particularly on encouraging a more widespread culture of transparency through registration of protocols for hypothesis evaluating real-world evidence studies. And there are already two major study registration sites, clinicaltrials.gov, which is intended for trials, and EU PASS, which is particularly geared for post-authorization, usually safety-oriented studies for European regulatory purposes. But for HEOR, HTA, and other data science researchers who don't already have a mandate or workflow for study registration, this registry is a simplified platform that is specifically focused on real-world evidence studies. So the registration process has been streamlined to include only a limited set of questions about the study and investigators, followed by the required upload of a protocol. The registration is automatically linked to a project space that allows registrants to store and share code, appendices, and other supporting materials related to the project, all of which comes with the citable DOI that's linked to your ORCID ID. There's also an embargo feature so that the protocol can be held privately while the study is being implemented. In phase one of the site, the uploaded protocol is going to be allowed in any shape or form that the investigator wants to use. But in phase two, the intent is to become more stringent in the standard for uploaded protocols to try and increase the usefulness of registered study information. And the hyperlink to the registration site is shown on this slide. So thanks for listening. Here's some references for the selected efforts that I mentioned today, and feel free to reach out if you have any questions.
Thank you so much, Shirley, for a very interesting talk. I'm happy to open the floor, or the virtual floor for questions. Either please feel free to use the hand function or the chat function. And while folks are, preparing some questions, I had one question. I think you answered it a little bit at the end, but I want to, circle back to it a bit, just in terms of the protocol registration process, because I think it's a key feature, and we've seen it in trials, its importance. But I guess one of the challenges I think that we've had, in a real world evidence perspective, is that, if we put the full protocol out there, in the, the possibility of, I don't want to say getting scooped, but, and you touched on it at the end in terms of, the inclusion of embargo feature. So I guess, can you maybe just expand upon that a little bit? Because like with trials, we're not worried about getting scooped. If there's a $20 million trial, no one's going to turn around and scoop that right away. But for when there's so many databases out there, it's a possibility. So can you maybe just comment on that a little bit further? Like is it a indefinite embargo, or do people just have a fixed amount of time to before it becomes publicly available? Because I'm thinking particularly for things like PhD theses, where studies do take inherently a little bit longer, where that could be particularly valuable.
Yeah, I think it was a concern that was raised by multiple people about the registration process, including pharma companies that were very concerned about getting scooped with their real world evidence studies. And so I'd have to double check, but I believe what the current setup is, you can embargo for up to 3 years. And then I'm not sure if you can renew that embargo after that or not.
Okay,
Does
wow,
that address the question?
Yeah, no, it does. That's actually, it's a much longer embargo period than I thought. I was just even thinking just, you know, whether it's a year just to get, time, but also given the data delays, to get, data sometimes, I think that does make sense. Any questions from the group, either using the hand function or the, Robert has a question.
Hi, thanks, Chris. Thanks, Shirley, for a fantastic talk. That was really interesting to watch and give me a lot to think about. What I guess I'm going to start with an observation, which I think is perhaps under-recognized in the reproducibility world, is that you almost didn't talk at all about analytic code. Your focus was primarily on reproducibility of the study process, which I think, based on our experience reading papers, the study process is what's important, in that I'm confident that if we can figure out what the anchor time points are and the anchor events are and how the variables are all measured and so on and so forth, that with the level of detail you described, a group like ours could reproduce a study well, even if we used use our own programs. I guess I'd just appreciate your thoughts on that, and perhaps, I don't know if it's fair to compare and contrast, but compare what you've talked about today with approaches like, I guess I would say Odyssey, I perceive as being much more focused on reproducibility from the context of the code or the algorithms or the computing package that's being used to develop the results. Here, you seem more focused on the protocol, again, the key points in the study, and processes, and so I guess if I'd appreciate to hear your thoughts on that.
Yeah, I think there's different types of reproducibility, and one is computational reproducibility, which is, I think, what you were describing as the alternative, and we were focused on independent reproducibility because that means that the study choices, the scientific choices, have been communicated effectively, so someone else would understand them and be able to do it. If you understand what was done, then you can assess, does it make sense? Are these good choices? And do I want to change something that doesn't make sense, to see what happens? When you have computational reproducibility, yes, you will get the same result to the nth decimal point, but do you know what happened? Do you know what's going on underneath the hood? And that's sort of where, I guess, it's important, like you want it to have computational reproducibility, but that's not enough. It gives sort of, at least in my opinion, a false sense of transparency, because you can get the same result without knowing what's happening, if that makes sense.
Yeah, I think we're on the same page here. I think, we probably need to do a better job of building reproducible code chunks that can do things over and over again, so that that if you're starting with inputs X, Y, Z, one outputs A, B, C, that you can get that. I think we could do better with kind of packaging up code, but I have the same skepticism that, if you give me a study that's defined sort of in an ambiguous way, and I'm not sure what the decisions are, this is the typical paper we get in our journal club where, we can't tell what the anchor times were, and we couldn't reproduce it if you gave us the data. I'd like to be able to get to that point first, to say, okay, I can reproduce all the decisions like you said, and I can interrogate those decisions. And then, would be nice if at that point we had sort of plug and play code to run things. But again, I think I agree with you. I think too much emphasis perhaps in the reproducibility world is on the code and the algorithm side of things, and not enough on the reproducing the scientific process, I think is how you described it.
Rob, does that speak to, I'm thinking a little bit, from some of our experiences in CNODES, where the importance of the analytical protocol and where it bridges both, a scientific protocol that could be interpreted in a few different ways, and SAS code that is often, can often be set up very specifically for a particular data source, and where the SAS code in and of itself may not be entirely informative given the nuances of how different people program and the different data sources. And should we be thinking a bit about those analytical protocols and as a key source of transparency?
I think so. I think they sort of form that in our logic. They form that step of providing the decision-making process with a little more detail, or sufficient detail, ideally, that you hand that analytic protocol to 10 analysts and you randomly assign them different data sets, you should get the same answers back or the same process back, because it should be transparent enough. And it's, it's little things like, I think, Shirley, you may have mentioned this, like, which set of inclusion-exclusion criteria do you run in which order? You're never able to figure that out from a paper, but when reproducing things, and the code for inclusion criteria is straightforward, but when reproducing things, understanding the rationale behind that decision and making sure you understand the order of inclusion, I think is really, really important.
Yeah, it can make a big difference in your sample size and who's included.
Sammy.
Yeah, Shirley, thank you very much for this talk. This is extremely important work that needs to be done to better understand the real world studies. And there are so many of them that are being published now. I think we need some clarification into this. I just want to pick up on the point that Robert brought up with an anecdote of of some examples of in my career. So a few years ago, we had critiqued a whole set of observational studies that all had immortal time bias in the relationship between metformin and cancer. And one of the authors, in fact, an author of one of the very first studies, looked at that paper. And in our paper, we said that the proper way to do this is either by analysis using a Cox model with a time-dependent definition of exposure, or by redesigning the study properly so that you account for this immortal time. And the authors of the paper, and we invited, by the way, the authors of all of the papers to redo their analysis and properly account for this bias. And one of the authors for one of the papers actually did that. And they published the second paper again in the same journal. And in there, basically, it was essentially the same paper, but in the statistical analysis, they said, we conducted a Cox proportional hazards model analysis using metformin use as a time-dependent exposure variable. They did that, and the results were identical to the very first one. And I think to talk about Robert's point is that you may say that you are using a Cox model with time-dependent exposures, but you may not know exactly how to do that. And again, it is not obvious to do certain tools of analysis. It's easy to write them, but it may not be obvious for the analyst to actually apply them. And I think this is probably one of the aspects that Robert was addressing as well, is that your protocol and your analytic protocol as well can be very specific. but the execution of it may be missing somewhere. And we have seen that in many, many papers where more and more you now see, to avoid immortal time bias, we use a Cox model with time-dependent exposure. This is basically a sentence that we are seeing more and more, and we are never sure whether they actually did it or not. So as reviewers, we ask questions, but we're never sure. So I think your work is extremely important, and there is other components there that will need to be teased out as well to make sure that your repeat exercise is an actual repeat exercise and is not a correction for flawed studies that may not have used the tools properly.
Thanks, good points.
Actually, following up on Sammy's comment, in terms of repeat, you guys have done an astronomical amount of work, replicating all these studies. I don't know. What's next for the initiative? Is there just having replicated, what was it, 125 studies? Do you have any? Are there any next steps planned for that initiative?
So there's just trying to push the transparency aspect with the protocol template and extending the visualization framework. We're also working on some robustness evaluations for some studies that we're asking essentially very similar questions to see the impact of different choices and trying to in a structured process to empirically evaluate how that contributes to variation in estimates when applied in different databases.
Actually, just I guess one question for repeat is when you were reaching out to authors to clarify certain aspects, what was the response like? Like I know when we're doing systematic reviews and we email authors for clarification, where our success rate is not great. What was the response like for in repeat?
Okay, I'm not going to get these numbers exactly, but about half of the people responded at all. Among the people who didn't respond, I'd say maybe half of those people, their emails had changed. So we're not able to follow up with them. Among those that did respond, probably, I don't know, a third to half. Some of them just responded to say, no, thank you, we don't want to respond. Some of them responded and gave not very helpful responses to our questions about the stack of assumptions that we made when trying to reproduce their study, because we laid it out. These are your results, these are our results, and these are the assumptions we made, A, B, C, D, E. And then there was like a really wide range among the remaining. There's some people that one person actually within 2 hours of the research specialist reaching out came back with code and responses point by point to each of the assumptions that we had laid out. On the other end of the spectrum, we had one person respond back with very angry accusatory emails saying that we were accusing us of research misconduct, essentially, and saying like that, how dare we, how could we, and just creating a big stink about it. So it's really a wide range, and I'd say very, very small proportion came back with responses that were actually responses to the question about our assumptions.
Perfect. Thanks for the clarification. Any other questions from the group? Going once, going twice. Okay. If not, I just want to thank you again, Shirley, for a very interesting talk on a really important issue, and I think it's given everyone lots to think about. And thank you so much for taking the time for today's presentation. And I'll welcome everyone to join us again next month for our next talk in the CNODES virtual seminar series.
Thank you, Shirley.
Thanks.